Alright, in this video we're talking about counting techniques. So first of all, let's take a look at how to calculate probability of an event by counting the frequency. Let me pull out the markers. Now what do we have here? If the capital N represents the number of outcomes in the sample space, and N of A is the number of outcomes contained in event A, then the probability of event A is equal to the number of outcomes contained in an event A divided by the capital N. So actually this idea is quite similar to the idea of relative frequency as what we learned in the previous videos. We know that relative frequency is equal to the frequency of a category divided by sum of all frequencies. And this is very similar to the idea of P of A, probability of A, which is equal to N of A divided by capital N. So in other words, if we want to find out the probability of event A, we just need, first of all, we want to find out the number of outcomes in the sample space, and then we want to find out the number of outcomes contained in an event A. So that's pretty much the idea of calculating the probability over here. Now, once we know that, let's take a look at the product rule for the outer pairs. So, of course, outer pairs means if we have two numbers, A and B, if A is not equal to B, then the outer pair AB is completely different from the outer pair BA. Okay? Because if the outer of those two numbers in the outer pair are different, so those two outer pairs are completely different. Now, once we know that, let's get into the tree diagram first, and then we'll come back to the proposition part. Let's take a look at tree diagram. So as what I just mentioned, if we have if A is not equal to B, then AB, the outer pair AB, is completely different from the outer pair BA. Okay, why we know this? Let's see. Oh, in this case, A could be four numbers: A1, A2, A3, and A4. And B got four possible values as well: B1, B2, B3, and B4. So we want to see how many outer pairs we can have. Okay, let's take a look at the options. First of all, I'll write down the value of A, and then value of B, and then AB, the outer pair AB. So first of all, let's select a value for A. Of course, there are four choices for the A. It could be A1, could be A2, could be A3, could be A4. Right? We get four choices. And then let's take a look at the choices for B. So as we see, whatever the value of A is, there are always four choices for the value of B. So if A is A1, the B could be B1, B2, B3, and B4, right? If A is A2, B could be B1, B2, B3, and B3 and B4. If A is A3, then the value of B could be B1, B2, B3, and B4, right? If the value of A is A4, then the value of B could be B1, B2, B3, and B4. Now let's take a look at the outer pair AB. So if A is A1, the B could be B1, so the outer pair would be A1, B1. And then if A is A1, B could be B2, so the outer pair would be A1, B2, and then A1, B3, and then A1, B4. If the value of A is A2, of course the value of B could be B1, B2, B3, B4. Then the outer pair AB could be A2, B1. and then A2, A2, B2, and then A2, B3, and then A2, B4. Of course, if the value of A is A3, the value of B could be B1, B2, B3, B4. So it's going to be A3, B1, A3, B2, A3, B4, B3, A3, B4. And then if the value of A is A4, and the value of B could be B1, B2, B3, B4, so the outer pairs could be A4, B1, A4, B2, A4, B3, and then A4, B4. Now let's see how many other pairs we could have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we get 16 outer pairs. We get 16 possible outer pairs in total. So where's the 16 coming from? That's coming from the four possible values of A times the 4 possible values of B. So 4 times 4 gave us the 16 over here. And this is called tree diagram. The whole thing over here is called the tree diagram. Now, once we know this idea, once we know that this 16 is coming from 4 times 4, now let's get back to the proposition here. If the first element or object of an ordered pair can be selected in n1 ways, and for each of these n1 ways, the second element of the pair can be selected in n2 ways, then the number of pairs is n1 times n2. Okay? I have showed that why this is n1 times n2. This is pretty much the same as we have 4 times 4 over here, which is 16. Alright, once we know the product rule over here, let's take a look at this example. The problem says a homeowner doing some remodeling requires a homeowner doing some remodeling requires the service of both a plumbing contractor and electrical contractor. If there are 12 plumbing contractors and 9 electrical contractors available in the area, in how many ways can the contractors be chosen? So first of all, we're looking for the number of ways that the contractors could be chosen. So we think of this one by one. First of all, we think how many choices we have for the plumbing contractors. It's 12, right? And for each of the plumbing contractors, how many choices we have for the electrical contractors? It's 9, right? So that would be 12 times 9, which is 108. So if we denote the plumbers by P1 through P12 and the electricians by Q1 through Q9, then we reach the number of pairs of the form PI, QJ, with N1 is 12 and N2 is 9. The product rule is N is equal to 12 times 9, which is 108. Actually, whatever for the homework problems are on the test, if you show me this thing, you'll get the full credits. You don't have to do that. Okay, this part we denote the plumbers by P1 through P12 or the Q1 through Q9 for the electricians. You don't have to do that at all. So what you need to show me is to give me N is equal to 12 times 9 is equal to 108. You will get the full credits if your answer was right. That's for the example 2.17. And let's take a look at this example 2.18. And this is coming from the textbook as well. The problem says a family has just into a new city and requires the service of both an obstetrician and a pediatrician. So there are 2 easily accessible medical clinics, each having 2 obstetricians and 3 pediatricians. Now the family will obtain maximum health insurance benefits by joining a clinic and selecting both doctors from that clinic. In how many ways can this be done? So we are looking for in how many ways this could be done. First of all, I will say we're gonna think of this one by one, right? First of all, we wanna select a medical clinic. How many choices we have for the medical clinics? We have 2, right? There are 2 medical clinics, so that would be 2. Once we select the medical clinics, we're going to select the obstetricians. How many obstetricians we have? We have 2 obstetricians, so we times 2 over here because we got 2 choices. Once we select the obstetrician, and then we're gonna select the pediatricians. How many choices we have for the pediatricians? We have 3 of them, so times 3. So which is 2 times 2 times 3, which is 12. Now let's take a look at the answer given here. Denote the obstetricians by Q1 through O1 through O4, and the pediatricians by P1 through P6. Then we wish the number of pairs OI or PJ for which OI and PJ are associated with the same clinic, because there are 4 obstetricians and 1 is equal to 4. Actually, the 4 obstetricians is the total. We get it's coming from the 2 times 2 over here. And for each, there are 3 choices of pediatricians. So N2 is 3. Applying the product rule given as A1, N is equal to N1 times N2 is 12 possible choices. Actually, I will encourage you to think of this kind of question by this way I gave you over here. Just think of one by one. First of all, we're gonna select a medical clinic, and then once we get the medical clinic, we're gonna select the obstetricians from those 2 obstetricians in the clinic, and then we're gonna select the pediatricians from the 3 pediatricians in the clinic. I will encourage you to think of it in this way. Okay, I think this is more clear than the answers given over here. All right, so once this is clear, let's take a look at the general form of the product rule. Suppose a set consists of ordered collections of k elements. So we get k elements over here, and that there are n1 possible choices for the first element. For each choice of the first element, there are n2 possible choices of the second element, and so forth. For each possible choice of the first n minus k elements, there are nk choices for the kth element. Then there will be n1 times n2 times until nk possible k tuples, right? So this is pretty much just a general form of the problems of the product rule we went over here. So in the first example, we got 2 elements, and in the second example, we get 3 elements, and in this case, we could have more than 3. All right, we could have we could have k possible elements. So this is just the extension of the product rule we just went over up here. So once this is clear, let's take a look at this example 2.19. So this is a continued this is coming from the example 2.17. So suppose the home remodeling job involves first purchasing several kitchen appliances. They will all be purchased from the same dealer, and there are 5 dealers in the area. So with the dealers denote, and we wanna find how many different ways that the dealers and the contractors could be chosen. So we don't find n. First of all, as what I mentioned before, we want to think of this kind of question one by one. First of all, let's say how many choices for the kitchen appliances. We have 5 of them, right? That would be 5. And then once that, we want to select the plumber. What is it? is a plumbing contractor, and we get 12 of them. And then we wanna select the electrical contractor. We have 9 of them. So after the 5 here, we want to multiply by 12 and then multiply by 9. Okay, we got a 5 kitchen appliance dealer, and we got a 12 plumbing contractor, and we got 9 electrical contractor. So this would be equal to 540, and which is exactly same as what given here. Okay. So once this is clear, let's take a look at the example 2.20. If each clinic has both 3 specialists in internal medicine and 2 general surgeons, and then we want to say how many ways we have in total to choose those doctors. So first of all, let's say, as what I just mentioned, we want to think of it one by one. First of all, we go ahead to select a clinic, which is 2. So 2, and then times 2 for the obstetricians, and times 3 for the pediatricians, I think. Yeah, pediatricians. And then we're going to select the specialist. How many choices we have for the specialist? We have 3 of them, and times 3. And then we go ahead to select the surgeons, general surgeons. How many of them we have? We have 2, so we times 2 at the end. And then this would be equal to 72, which is exactly the same as is given here. Once again, I will encourage you to think of this way, to think of one by one. Clinics, and then obstetricians, pediatricians, and then specialists, and then the general surgeons. Okay, I think this is easier to understand. Okay, now once this is clear, let's take a look at the permutations and combinations. Now, definition: an ordered subset. An ordered subset is called a permutation. The number of permutations of size k can be performed from the n individuals or objects in a group will be denoted by p sub kn. Okay, k is the size can be performed from the n individuals. So first of all, let's take a look at this simple example. If I have, let's say, 40 numbers, 1, 2, 3, and until 40, and I want if I want to arrange those 40 numbers, how many different ways we have? Okay, so let's think of those 40 numbers one by one. Okay, so how many choices do we have for the first number? The first number could be any one number from those 40 numbers, right? So we get 40 choices for the first number. And then how many choices we have for the second number? Now how many numbers left now? I think there are 39, right? We got 39 numbers left. And how many choices we have for the third number? We got to think of how many numbers left now, right? So we get 38 of them left. So we have 38 choices for the third number. And so forth until the very last one, or the 3 times 2 times 1. Okay, so this is the last number. We only have 1 choice for the last number, and we have 2 choices for the second last number, and we have 3 choices for the third last number. And this is equal to 40 factorial. This is called a 40 factorial. In a general form, if we have n factorial, then n factorial would be equal to n times n minus 1 times n minus 2 times until times 2 times 1. That's n factorial. Okay. Now, Let's take a look at the combination. An unordered subset is called a combination. One way to denote the number of combinations is a C sub kn, but we shall instead use the notation that is quite common in probability books. That's the bracket. We have n on the top and k on the bottom. That read n choose k. So the main difference between the permutation and the combination is we gotta say if it's an ordered subset or it is an unordered subset. Okay, if we should think of the order of the possible outcomes, we gotta think of the permutation. If the order of the numbers doesn't matter, we gotta think of the combination. Okay. Now let's take a look at this example over here. How many ways are there to give 3 different pens to 3 out of 7 students? So we have 7 students in total. 1, 2, 3, 4, 5, 6, 7. We got 7 students in total, and let's say I have A, B, and C, 3 different pens. If I want to give the A to one of those 7 students, how many choices we have? I have 7 choices, right? Because it could go to any one of them. After A, and if I want to give the B to the rest of them, how many choices we have? It's going to be 6. Right? After B, and if I want to give the C to the rest of them, how many choices we have? It's going to be 5. Okay? So this is equal to the permutation P37. Okay? This is equal to 7 times 6 times 5. What is the permutation? Because the order matters. For example, if the pencil A gives the number 1 students and pencil B gives the number 2 students. So this is different from B goes to number 1 student and A goes to number 2 student. They are different. That's why I said the order matters over here. And actually we can to make the calculation easier for the future, we want to put this thing in a form of factorial. So what we can do here is 7 times 6 times 5. So what we're doing here, we are multiplying 4 factorial by both top and bottom. And then on the top, we have 7 factorial, because 7 times 6 times 5 times 4 factorial is 7 factorial. Divided by 4 factorial. And what is the relationship between the 4 here and the 7 and the 3 over here? So 4 is equal to 7 minus 3, right? Let me clean this over here. So it's going to be 7 factorial and 7 minus 3 factorial. And we know that in the general form, 3 is the k and 7 is the n. So this would be n factorial divided by n minus k factorial. And this brings us to the proposition over here. The p sub kn is equal to n factorial divided by n minus k factorial. So once you get the question, first of all, you got to think of if the order matters or not. If the order matters, then we got to think of the permutation. Now let's take a look at the example 2.21 here. There are 10 teaching assistants available for grading papers in a calculus course at a large university. The first exam consists of 4 questions, and the professor wishes to select a different assistant to grade each question. Only 1 assistant per question. In how many ways can the assistants be chosen for grading? So first of all, we got to think if it's a permutation or combination. So we want to say that if the order matters or not. So first of all, we get 4 questions. Let's say Q1. Let's just think of two questions, okay? Let's say Q1 and Q2, two questions, and we get a student 1 and a student 2. So if we got to say if student 1 grading question 1 and student 2 grading question 2, is this different from student 2 grading question 1 and student 1 grading question 2? They're different, right? Because we have different students grading different problems. So those two groups are completely different from each other. That means the order matters, and we want to think of the permutation. Okay? So the permutation would be P sub 410. So based on the proposition we have here, it's going to be the n factorial, which is 10, n is equal to 10, and the k is 4. So on the bottom, we have m minus k, m minus 4. So which is 10 factorial divided by 6 factorial, which is equal to 10 times 9 times 8 times 7, which is 50, 40. So why this is equal to this fraction over here? So actually we can simplify this fraction. So we know that 10 factorial divided by 6 factorial. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 and then times 1. And we know that 6 factorial is 6 times 5 times 4 times 3 times 2 and then times 1. So those 6 numbers from 6 to 1 are the common factors between top and bottom, and they'll be cancelled out. So this whole fraction would be equal to this 10 times 9 times 8 times 7. And that's how we got a 50, 40 over here. Actually, we can think of this kind of question in another way. Just like what I mentioned previously, we can think of those 4 questions one by one. So for example, we have, I'll put it over here. So, we don't want this over here. So we got a question 1, question 2, question 3, and question 4. Right? So if I gave each of the question to a different assistant, how many choices do we have for the number 1? So if I gave the question 1 to 10 to one of the 10 students, how many choices do we have? We have 10 choices, right? And after this, I want to give the second question to one of the rest 9 students. How many choices I have? I have 9 choices, right? Because different problems should be graded by different students. And then after that, I want to give the question 3 to the remaining students. How many students left now? 8. So we get 8 times 8. And then I want to give the number 4 to one of the remaining students. How many students left? 7. So times 7. And this would be equal to 50, 40, which is exactly the same thing as what we get over here. Okay, that's pretty much how to solve this kind of problem. Okay, now let's take a look at this example over here. How many ways are there to select 3 students out of 7 on a project together? So this time we want to put those 3 students in one project, okay? So as what we just went over, we want to think of the permutation first, right? So P37, if we want to find out how many differences we have. But the problem here is we want to put them in one project. Now my question is, does the order matter over here? So if I have project over here, the circle represents the project, and I select the students A, B, C. So that means the A, B, C work on the project. And if I give another circle, that means B, A, C. Are they different? No, they are equivalent in this case because both of them represents the student A, B, and C working on the project. The order doesn't matter, right? But the permutation here contains those kind of difference. the permutation contains the different orders here. So if we want to balance that, we wanna divide by 3 factorial. Because if we want to rearrange those 3 people, we have 3 factorial different ways. So it could be A, B, C, and then A, C, B, and then B, A, C, and then B, C, A, and then C, A, B, and then C, B, A. So we have 3 factorial different ways to arrange those 3 people, but the problem here, the point here, they all represent the same thing. They all represent those 3 students working on this project. Okay. Now, as what we just mentioned, we know that the permutation 3, 7, that is equal to 7 factorial divided by 4 factorial. And we need 3 factorial on the bottom over here. Okay? And then this represents 7 choose 3. And that's called the combination. Okay? If we put it in a general form, we have, of course, the 7 over here is the n, and the 3 means k, and the 4 represents n minus k. So if we put it in a general form, that would be, and of course this is n, this is the k. N choose k would be equal to the permutation kn divided by the k factorial, which is equal to n factorial divided by k factorial times n minus k factorial. So once again, the main difference between the permutation and the combination is we want to make sure if we are looking for an ordered subset or an unordered subset. Okay? If we are looking for the ordered subset, we can think of the permutation. If we are looking for the unordered pair set, we can think of the combination. Okay? They are completely different. Once again, the reason why we should divide it by 3 factorial over here is because there are 3 factorial different ways to arrange those three students over here. But the problem is all those 3 factorial difference represent the same thing. They all represent those 3 students working on the project. There's nothing different. Okay. So basically, if we put this thing in a general form, we will get a permutation kn divided by, let me write it down. So of course, if we think of the combination, we want to think of n choose k, and that would be the permutation kn divided by the k factorial. And this would be equal to the n factorial divided by k factorial, and then divided by n minus k factorial. Oh, factorial is supposed to be outside the parenthesis. I'm sorry. Of course, So this is exactly the same as given over here. That's how I find the combinations. Notice that n choose n is equal to 1, and n choose 0 is equal to 1, since there is only one way to choose a set of all n elements or of no elements. And n choose 1 is n, since there are n subsets of set 1. Right, once we see the difference between the permutation and the combination, let's take a look at those 2 examples, and I think those 2 examples will make everything clear. So the problem over here says that particular iPod playlist contains 100 songs and 10 of them are by the Beatles. Suppose the shuffle feature is used to play the songs in a random order. The randomness of the shuffling process is investigated by this. Does your iPod really play favorites? And what is the probability that the first Beatles song heard if the fifth song played? Now, first of all, we are looking for the probability over here, and we want to think of the relationship. The probability of A is equal to n of A. Oh, what is that? We want to say the probability of A is equal to n of A divided by the n. Of course, n of I represents the frequency of event A, and n represents the possible outcomes, the number of possible outcomes in the whole simple space. Now let's take a look at what we're looking for. We are looking for the probability. I don't know why this doesn't work well. So let me rewrite it down. We are looking for the probability that the first Beatles song heard is the fifth song played. So first of all, based on the formula given here, if we want to find a probability, we want to think of the simple space first, right? So let's think of the case one by one. Let's say, okay, how many possible outcomes we have in total in general, okay? So if we are playing the first song, how many choices we have? In this case, since we're thinking of the bottom here, we don't have to worry about if it's coming from Beatles or not. We just need to say, okay, this song is coming from the 100 different songs over here. So how many different choices we have for the first song? We have 100, right? Because there are 100 songs in total. And then how many choices we have for the second song? It's gonna be 99 because there are 99 will be left. Okay. Then how many choices we have for the third song? That would be 98 because there would be 98 songs left. And then how many songs we have? How many choices we have for the third song? That would be 97 because there would be 97 songs left. And after that, how many different choices we have for the fifth song? We have 96. Right? So the bottom would be the multiplication of those 5 numbers. And then let's think of the top. So if the first Beatles song heard if the fifth song played, that means the first 4 songs are not coming from the Beatles. Right? The first 4 songs are not coming from the Beatles, right? And we know there are 100 songs in total, 10 of them are by Beatles, that means the 90 of them are not coming from Beatles. Then, as what I just said, the first 4 songs are not coming from the Beatles, right? So, first of all, the first song is not coming from the Beatles. How many choices do we have for the songs not coming from the Beatles? It's gonna be 90, right? We have 90 songs come from the Beatles. And then, for the second one, the second song is not coming from Beatles. And how many songs left are not coming from the Beatles of the first one? There will be 89 of them left. And then times the third song. Alright? So how many songs left are not coming from Beatles? It's 88, right? And the fourth song is not coming from the Beatles either. And how many songs left not coming from the Beatles? 87. 87. This is 87. Let me click this real quick. 87. And then the fifth song. The fifth song is coming from the Beatles, right? So if it's coming from the Beatles, and this is the very first Beatles song, and how many choices we have? We have 10 choices because there are 10 of them are by the Beatles. And then if you type the whole thing in your calculator, you will have the probability is 0.0679. That's how we find the probability in this question. Okay, I actually, this is a sort of about permutation, but I will encourage you to think of it in this way. Just think of it one by one. First of all, find out the bottom, find out the how many difference we have in total, and then we go ahead to find out the frequency of the first song heard is the fifth song played. The first Beatles song heard is the fifth song played. Okay, now once this makes sense, let's take a look at the very last example of this part. A university warehouse has received a shipment of 25 printers, of which 10 are laser printers and 15 are inkjet models. If 6 of those 25 are selected at random to be checked for a particular technician, what is probability that exactly three of those selected are laser printers, so that the other 3 are inkjets? So first of all, we want to think of that probability. I don't know why this doesn't work well. The probability of A is equal to y, n of A divided by n. So first of all, we want to think of the we want to think if there's a permutation or combination. So if this is a combination, why? So if we select, for example, we select those 3 laser printers. So I will say we are selecting number 1, number 2, number 3 is exactly the same as we're choosing number 2, number 1, and number 3, right? Because we're just checking if they have problems or not. So those 2 different groups represents the same thing, which is those 3 machines are being checked. So since we are thinking of combinations, and then let's once this is clear, let's take a look at how to find the probability. It's asking. So we're looking for that the probability. I don't know why. The probability exactly three of this selected are laser printers. Now, first of all, let's take a look at how to calculate. This is equal to. Now, let's take a look at the bottom first. So the bottom is that we want to say already how many difference we have to select 6 printers from the 25. And we know that this is a combination, so the total would be 25, choose 6. And then we want to say what the bottom looks like. So we want to say exactly 3 of those selected are laser printers. So which means we have 10 choose 3. That's for the combinations of the laser printers, because we have 10 laser printers in total and we want to select 3 out of 10. And then for the inkjets, so we have 15 inkjet models, and we want to choose 3 out of 15 as well. So it's going to be 15, choose 3. And that is equal to, so what we need to do next is just apply the formula. So this part would be 10 factorial divided by 3 factorial times the 7 factorial. This is 10 factorial times this part. The second part would be 15 factorial divided by 3 factorial and then 12 factorial. 12 factorial is coming from the 15 minus 3. And then divided by 25 factorial divided by 6 factorial and then times 19 factorial. 19 is coming from 25 minus 6. And then if you type the whole thing in your calculator and this, I put the answer over here, this is equal to 0.3083. Okay? So basically what we're looking for here, or what we're applying here, are the formula over here, the formula of the combinations. Okay, I hope this makes sense to you. And I don't know why the iPad doesn't work well today, and I apologize for that, and I will try to fix it afterwards. All right, that's pretty much all about 2.3.